Hi guys. Today is a second session in our security award. I'm Lucas Nowatkowski, I'm your host, and next I want to introduce you the Moritz Eckert, Chief Architect, Edgeless Systems GmbH from Germany. He serves as a Chief Architect in Edgeless System and company dedicated to making confidential computing more scalable and accessible to everyone. Parodygenic and less. In 2020, he conducted extensive research on cyber reasoning systems in Eurocom and UC Santa Barbara. Moritz has presented his thinkings at the various reputable conferences, including Usenix Security, RSA Conference, KubeCon. He is highly regarded field and experience insights the confidential computing, demonstrating strong comments to the advertising critical technology. And today we're gonna go with cloud, with confidential cloud and safeguarding sensitive data in K8s. Then we are welcome the Moritz Eckert, and he will be able to talk more about himself. And go forward, Moritz. Thank you.
Thank you very much, Lucas, for the introduction. Yeah, not talking so much about myself, hopefully, more about the topic. But yeah,
okay.
Looking
forward.
But
maybe it will be even fine if the people will know who they are.
Yeah, right. I'll give a short intro to myself for sure.
Yeah. And I leave you and bye-bye.
Thank you, Lucas. All right. Let's start the presentation. How does it work? Here. Sorry, I thought. Can we see the presentations already?
No, not yet. You should share the screen.
No, I uploaded the slides and they are in the backstage now. Not sure how to activate them.
Okay.
But I can also share my screen.
At the stage, I will add it to stage.
Yeah,
then maybe
perfect.
It will be better. Then
there they are.
Keep going. Bye-bye.
Perfect. No, thanks. All right. Yeah. Let's get going. Lucas already gave the introduction. We're going to talking about confidential computing and how we can safeguard our code and data in the public cloud using confidential computing. Oops. Just briefly about myself, as Lucas said in introduction, I work as a chief architect for a startup from Germany called Edgeless Systems, where we build open source software for this new technology called confidential computing. We are based in Bochum, which is the west of Germany, and we are very active in this field of confidential computing, also hosting the largest conference there. And since this is a very cloud-focused topic, we are also active in the cloud-native related conferences, and we are a part of the CNCF, the Cloud Native Foundation, and so forth. So much about Edgeless. And now I want to go a bit more into the background of what is confidential computing, what problem does it solve, why is it interesting to make use of confidential computing, and then a more hands-on approach in the second part of this talk, where we'll talk a bit more about what does it feel like to use confidential computing, where does it apply, where is it visible for application developers, platform engineers, cloud engineers, and so forth, right? Where does it apply, how do we use it? And in the end, I will talk a bit more about the use cases and some more practical examples, so you get a better feeling of what it does. So in the end, you will be equipped with a good understanding of where's confidential computing, how does it help me? And if I want to use it, what would be the next steps? Right. So usually when we talk about the cloud, we think of this nice world, right? There's rainbows in the sky, but there are practical reasons of why people move to the cloud. For sure, it's a lot about reducing CapEx and accelerate innovation. I think a good example right now is the whole AI hype and all of this AI wave that's hitting us, where people want to quickly innovate and integrate this technology, and they don't want to build up everything from scratch, build their own data centers, get the required compute power, the latest GPUs, and so forth. They actually just want to consume services. They want to consume infrastructure to implement, integrate, and innovate on this technology. And there might be other reasons for moving to the cloud, but I think this is a good example that represents well a lot of these use cases where people actually consume cloud computing. But the other side to cloud computing is, especially if we are here in the cybersecurity conference, is this security perspective, right? There are different threats now we need to deal with. There's a different threat model. And also, especially in Europe, we're dealing with a lot of privacy sovereignty issues. For a lot of industries, can talk at least for Germany, we have a lot of hurdles certain industries need to go through to actually make use of cloud computing. This could be the public sector, this could be healthcare, this could be defense or even finance. Anything that's dealing with sensitive information essentially always has these additional steps and processes I need to go through, if at all they are able to use cloud computing. And because of that, because it's tough and it's cumbersome to go to the cloud for these industries, this is a bit of where the need and one of the needs for confidential computing comes from. So in a nutshell, what the underlying problem here is that we are processing our data, our code on essentially somebody else's computer. And because this is a remote and uncontrolled environment, this could be anywhere in the world, and there could be anything running on that system, and anybody could have access to this system. So it's completely hostile and uncontrolled, at least from this trust model perspective, where I want to control the access to my data. So this is a bit of the challenge. How can we establish trust in our code and the security of our data in this threat model, in this environment? And the idea of confidential computing essentially is that we can create an isolated environment that's runtime encrypted. We'll see in a second of what this means. And completely shielded from the rest of this infrastructure. And that we have a form of verifying that these properties are true, even from a remote location. So we don't need to drive to the data center and physically ourselves defend the data, but there's actually some form of remotely verifying the security and privacy of our data that's being processed in these systems. Right, so how does confidential computing achieve this property? And fundamentally, confidential computing adds a new state of encryption to the data. So far, or right now, or before confidential computing, what we had is we had already encryption at rest. If we store data on a hard drive, there are different methods for ensuring that this data is stored encrypted. So at rest, we have our data encrypted. The same goes for in transit. Everybody that uses the web today will make use of TLS, transport layer encryption. So sending data through encrypted channels, also something that we've covered. What we haven't yet covered is protecting the data while it's being used. So when you have a cloud service, some workload running in the cloud, when it's processing your data, right, it does that in plain text. And this was the missing piece of the puzzle. And this is where confidential computing comes into play. Essentially, there are different ways of how this missing piece in a puzzle can be approached. Some of you might know homomorphic encryption, right, where we operate on encrypted data. So this is maybe an algorithmic approach to this problem. Confidential computing applies as slightly different. It's essentially a hardware-based solution, hardware-based technology, where we extend first of all, the processor, the CPU. There's an instruction set extension that essentially allows you to keep the data of a process isolated from all of the other processes on that chip, keeping the main memory, the data of your process, the pages, encrypted at runtime. So the memory engine has a key and encrypts all of the pages connected to that process. And there's a form of remote attestation. So the processor has a burnt-in secret, a private key that allows it to sign a report about your process. So essentially, the identity, the content of the memory pages, and some meta information about the processor itself, the firmware, and so forth. So there's a report, and the CPU can sign it with this key. And then there's a certificate chain that goes back to the hardware vendor. Let's say Intel, AMD. Yeah, ARM is a bad example since ARM doesn't really do physical silicon, but whoever processes this ARM chip, there's a chain back to the hardware vendor. And this allows to verify this attestation report actually belongs to a benign CPU, for example, from Intel. Right, so these are the properties, these extensions to the processor. And the first iteration of this technology was pioneered by Intel back in a couple of years back. I think in 2015, Intel released the Secure Guard extension, which was maybe the first real occurrence of a confidential computing CPU technology. SGX was based on an individual process, so you can isolate an individual process in the system with these features. Now, recently, Intel has announced a new extension called the Trust Domain Extension, TDX, which essentially, instead of isolating a process, we now go into the virtualization layer. So we isolate an entire virtual machine. We're not going to go into all the details why this change or why this new extension made sense, but essentially by going into different abstraction, this fits more into the abstraction we now have in the cloud, right? Where everything is virtualization based. If we can apply confidential computing on the virtualization layer, we can apply it more transparently and less invasive to the actual application. And how we're going to apply it, we'll see in the second part of this talk. But essentially, you need to think of this TDX now isolates an entire virtual machine on a system that runs on such CPU. And this virtualization-based approach was actually pioneered by AMD with their technology called Secure Encrypted Virtualization, short SAV. And now ARM also released a specification called Confidential Computing Architecture, short CCA. So there will also soon be ARM-based chips that have more or less an equal solution. So essentially, all of these server CPUs from these vendors now have these features where we can isolate and runtime encrypt a virtual machine, and we can get a form of remote attestation that allows us to verify that actually our VM, our virtual machine, was booted in this remote cloud location, and that it's protected, that it's isolated during its lifetime. Right? This is what we get. So if you look at the stack, the way it looks like is we have the hardware. So the cloud providers need the hardware there. They have their hypervisor layer. And now the hypervisor uses this instruction set extension to create a virtual machine. So let's say they take our image. For example, on AWS, you have the Amazon, what's it called, AMIs, the images. You take the image, the hypervisor takes this image and creates a confidential VM, an isolated VM by talking to the CPU, reserving all the pages, loading all of the pages for the operating system, or the first of all the firmware, and then the operating system, and so forth. Loads it all and basically tells the hardware to lock it down and shield it from any further access. And yeah, which means after this confidential VM has been created, there's no more virtual or no more horizontal or no more access from any other part of the system. So not the hypervisor, no other part of the infrastructure, no other virtual machine that's running on the same hypervisor can now access this confidential VM. They can also not access the memory pages. And due to the runtime memory encryption that the processor ensures, even if you have physical access to the data center, you will not be able to dump any kind of code or data that resides inside this isolated environment. Right. So this is basically the technology. And then there's the remote attestation that I briefly explained, where I can now, from inside the guest here, right, the operating system or the application layer, I can obtain an attestation statement from the CPU. So there's basically a new hypercall that's being passed on from the guest through the hypervisor to the hardware, establishing a secure channel to that hardware and obtaining an assigned attestation statement about the identity of the guest, of the everything that's inside the green box, signed by the CPU. And this I can now use to verify my virtual machine from a remote location. So I do a handshake with this report, establish a secure channel to that guest, and verify its identity. And from then on, I know, okay, this is really an isolated machine with the correct identity that I expect to be there, and I can securely process any kind of data inside. That's roughly the how this works. Now, recently, this has even been extended not only to CPUs but now to accelerators. NVIDIA has released similar features for their H100 line, and basically now there's a way for establishing a secure channel to the GPU, verify the properties of the GPU, so also that the code and data is isolated inside the GPU, that it's protected, and that that's actually the correct NVIDIA firmware, and so forth and so forth. You establish a secure channel, and then you can use the accelerator as part of this isolated environment. This is particularly important if we talk about AI use cases, where often we require GPUs. So in summary, that was the background on confidential computing. What we have is now we have a hardware-based solution for protecting our data in use, shielding our data from the rest of the infrastructure through a form of runtime encryption, isolation, and we can verify these properties through a form of remote attestation. And these features are available in the latest hardware CPUs from AMD, from Intel. They will also soon be available in ARM chips. And the good part about this is that because it's a hardware-based solution, it does not suffer from the same performance penalties, maybe such as homomorphic encryption. So due to this hardware-based approach, we see overheads in the single-digit percentages, depending a bit on the workload. And we can roughly, for most workloads, we can roughly neglect that and just use the infrastructure as usual. And the cool thing is it's already available on the hyperscalers, so AWS, Azure, GCP, and a lot of other smaller cloud providers. So they already have this infrastructure available for us to use. Now the question is, how do we use it? How do we make use of confidential computing if we want to benefit from these features? So we have this nice graphic where we basically see 3 levels of where confidential computing can be applied in a cloud scenario. The first level is maybe that we use confidential computing to replace systems that require dedicated hardware so far. And the first thing that comes to mind here is maybe key management. So there are offerings for, let's say, virtual HSMs, which basically implement an HSM completely in software. And this software is then isolated through confidential computing in a cloud environment. And you can basically run the HSM on commodity hardware. Yeah? So this basically replaces additional hardware requirements through confidential computing. But it does not add any new kind of isolation and security benefits to your workloads. This is where level 2 comes into play, where we say, okay, let's isolate an individual workloads. I mean, the most basic thing you can think of is you take this confidential VM, and if you're operating on a VM level, you ship and deploy your software on a VM level, for example, you can run your VM in a confidential VM. And if you have a monolith, you run this in a single VM, and this VM is then isolated through confidential computing. Same potentially can be applied to containers. We will also see this in the next part. Now, the level 3 is essentially what we say, or where I see this going towards, because in the end, we don't need this point solutions. We need to use confidential computing for isolating our entire environment, so that our entire application, whatever it consists of, let's say multiple containers, a key management system, a database, and so forth, that this all needs to be shielded as a whole, so that we have this end-to-end encryption, and that any data that's flowing through this application, whatever it's built up on, whatever the architecture looks like, is really isolated from the infrastructure. And basically, we need to think of more in an entire application deployment type of isolation, not those individual points. So this is a bit of more abstract of how confidential computing can apply it in more of a sense of where it can apply it architecturally. And we'll dive a bit of more into what this looks like in practice if we talk about a Kubernetes environment, so a Kubernetes stack. This just emphasizes a bit more on the fact of what we need to think of if we want to isolate our application, right? Where we have a microservice architecture, and this not only consists of one monolith, but multiple services. This doesn't necessarily need to be a containerized application. It could also be just that you have a monolith and a database, for example, right? But let's think of, we have 3 parts of application here: a web front and the application logic in a database. In the end, we need to connect them all together, right? All of these individual parts of application need to be encrypted, runtime encrypted, isolated through confidential computing. Then we need to attest them all. We need to individually attest them. So do this remote attestation procedure, verify their identity and their isolation properties, and then connect them together, establish secure channels, provide them with their configuration, provide them with a form of identity so they can authenticate each other, and so forth. So there's a lot of this in-between things we need to do. So in the end, our application gets shielded as a whole. So Kubernetes and confidential computing. So we saw confidential computing. We saw how and what it's in, how we can apply this in the different levels. Now we'll talk concretely about Kubernetes, since Kubernetes is more or less the de facto standard now as one part of our stack, as the orchestration layer in our stack. You don't necessarily need to be exposed to Kubernetes directly. It could also be that you consume any type of managed service on top, but underneath, often somewhere in the stack, there's a Kubernetes layer for scalability, orchestration, software lifecycle reasons. And so I think it makes sense to see how we can apply confidential computing in a Kubernetes stack, and what this means for your application layer and anything on top. Right. So if we take a look at a Kubernetes cluster, right? So I'm not sure if everybody's familiar with the Kubernetes terms. Usually in Kubernetes, we talk about a cluster as anything in our infrastructure. And this cluster usually consists of the actual compute resources, which we call nodes. So each node is usually one machine where parts of application are being scheduled on and run on. Yeah. And in a cloud world, usually every node is a virtual machine, right? So every node in your Kubernetes cluster is a virtual machine. And there are special nodes called the control plane, which basically host all of the orchestrational features of Kubernetes. So all the Kubernetes, the Kubernetes components itself, they run inside this control plane, like the scheduler, the API server, and so forth. And the control plane is just a special type of node, so it also runs inside VMs. And then our actual application in Kubernetes is usually packaged inside containers. And then Kubernetes schedules these containers in an entity called a pod. So pod is the smallest entity Kubernetes knows as one part of the application. And a pod can consist of multiple containers. But nevertheless, think of pods is where our application sits. This is our containers. And these are scheduled on the nodes. And all the scheduling part and all of this orchestration part is taken care of by the control plane. So the question is, where do we apply confidential computing? Remember, what confidential computing gives us is that it's based on the virtualization. It allows us to isolate an individual VM and encrypt that VM and attest that VM and so forth. And I see two sides of the spectrum here. One is more the more let's say native application, where we say, okay, where actually are we using VMs? We're using VMs on the node level. So why not applying confidential computing on the node level where we already are using VMs? So let's say all of our compute nodes, they run in confidential VMs. Our control plane runs in confidential VMs. Then we need to take care of all of these in between. So I'll show in a second what this means. But essentially, then we shield the entire Kubernetes cluster as a whole from the infrastructure. And the other side of the picture is that instead of focusing on where, from a technology and abstraction point of view, the best fit is, what do we actually want to isolate? In the end, what we want to isolate is our code and our data, specifically our data. So let's focus on isolating only our containers themselves. So in Kubernetes speak, only the pods, right? Only isolate the pods and keep everything else outside of this trust boundary. Everything else is untrusted. Now, then we need to solve this abstraction mismatch where we want to isolate containers, but the isolation property we have is VMs. And we'll see also in a second, we'll see how we can do that. Right, so this was the spectrum, right? These are more or less, there could be things in between, but more or less, these are the two approaches that we see right now of how we can apply this in a Kubernetes stack. First part of this now is focusing on the left-hand side, right? Isolating one cluster as a whole. So there's our project called Constellation, which is an open source Kubernetes distribution, which basically implements this form of isolation. It implements isolating a Kubernetes cluster as a whole. As I said, the idea is applying confidential VMs to all our Kubernetes nodes, including the control plane. This is the basic idea here. And then what we need to do additionally to make this useful and make this meaningful in terms of isolation and the security properties is anything inside is trusted, right? It's part of this, what we in the confidential computing speak, we call the trusted computing base, right? All of the components that are trusted because they're inside the green boxes, they're inside in the trust boundary. Because we isolate the control plane and the worker nodes and everything together, meaning that the Kubernetes components themselves, like the API server, the kubelet, if you're not familiar with the terms, doesn't matter, right? All of the Kubernetes components that take care of the orchestration and the scheduling of the containers, they are all inside this trust boundary. So they are trusted, which means from inside the cluster, I can use Kubernetes as usual. I can, this is lift and shift. There's no changes you need to do on the application and the deployment layer. Where you get in contact with confidential computing is on the platform layer when you need to deploy this Kubernetes cluster, this Constellation cluster. The operation teams needs to understand how they create this cluster. This can be done, for example, with Terraform or CLI tool, and then they need to do the attestation, verifying this remote attestation part, not for all of the individual VMs now, but for the entire cluster. And this is where Constellation is designed to make this easy and meaningful by basically implementing an image-based Linux approach. So all of the Kubernetes nodes, they have an immutable Linux image that's built for being attestable. So it follows a measured boot. So every chain in the boot chain is measured, giving you a clear report about the boot, which is part of this attestation procedure. And by being immutable, you ensure that what has been booted stays that way during the lifetime of that node. And then Constellation basically chains all of these nodes together as one cluster by verifying the individual nodes, providing them with credentials, joining them together in a cluster. And then, once this cluster is established, it takes care that also the already solved parts of encryption are also enabled for this cluster. With already solved, I mean the encryption in transit, so that all traffic between these nodes is actually encrypted by establishing encrypted channels between all of the nodes. That encryption at rest is enabled, so when you consume storage in a Kubernetes cluster, that this storage is transparently encrypted. And all of this is basically solved on the Kubernetes layer, right? Via all of the interfaces that Kubernetes provides, like the networking interface, the storage interface, and so forth. And by solving this all on the Kubernetes layer, the application on top is not really affected by this encryption layer, essentially. So this was the one approach, isolating the entire cluster. Cool thing here is we have lift and shift. Everything works as before. The downside maybe is that everything is isolated as a whole. So there's no isolation between the Kubernetes API server and my container. And that I need to approach this on the platform layer, right? I need to at least create this cluster and maintain this cluster in the cloud. So the other approach on the other side, where we want to isolate just our confidential containers, has slightly different properties or slightly different trade-offs. Here, we want to isolate it just an individual layer on top of the Kubernetes. So again, speaking about the trusted computing base, now all of the Kubernetes part is outside of this TCB, which means we don't trust the API server, we don't trust the kubelet, we don't trust any part of Kubernetes. This has two effects. One is we can deploy this on any Kubernetes, essentially, if it has the right hardware available, right? We can deploy this on a managed Kubernetes from the cloud provider. The downside is that we need to, we get closer to the application, and this also affects our application a little bit more than when we isolate the cluster as a whole. First problem we need to solve is how can we isolate a container based on a VM isolation? And the answer here is called, or one of the answers here is that there's a CNCF project called Confidential Containers that solves this by using the concept of Kata containers. I don't have the time to go into all the details, but long story short, essentially it allows you to isolate a container inside an individual VM. So inside your Kubernetes, now all of your containers are isolated by confidential VMs. This could either be done in a nested way, so all of your containers are running inside a nested virtual machine, or they're running in a remote virtual machine, which is somehow connected to this actual compute node, this actual Kubernetes node. Doesn't really matter about the details here, just understand that by using Kata containers, we can solve this abstraction problem. And then, we apply this to all of our containers that we want to isolate as part of this deployment. And then we need to solve the problems about that we don't trust the Kubernetes layer. So now I think of, you have your web front end, you have the application logic, you have maybe a database deployed inside this cluster. They're all isolated individually as a single container using this confidential containers project. And now we have this level 2, and we need to go to level 3. We need to connect them together so they can communicate securely. We need to attest all of these individual containers. We somehow need to establish, and I don't like to use this word, but we establish a service mesh, right? Where service mesh means they have a form of identity to communicate securely. They have all of the connections encrypted. And we need to somehow provide them securely with their configuration, right? If you think of Kubernetes, we don't trust the API server. We don't trust any parts of the Kubernetes state. So we cannot pass any information through that, either because this information contains sensitive information or because this information has effect on your application itself. Think of an environment variable that you pass to your database that somehow affects the database, right? You cannot pass that through the API server. You cannot pass us as part of your usual Kubernetes configuration YAML files. Or if you do so, you need to verify that they have been applied correctly. And this is what we solve with another project of ours called Contrast, which basically is somewhat of like the a tool for running confidential containers and solving all of these in-between problems, attesting them individually, providing them with credentials, providing with a policy mechanism that verifies that what you've configured as part of the API server configuration for your workload is actually ending up in that workload. And basically giving you a tool for deploying or isolating an entire deployment on a Kubernetes using confidential computing. So this is, in summary, this is the other side of the world where we isolate individual containers. It gets a bit closer to our application. We now have this more exposed to the operations team of the application itself, not of the infrastructure, not on the cluster side, but now we need to solve this more on the operations team of the application itself. And this has some effects in terms of using a tool like Contrast to make this manageable. But we isolate a much smaller part of our deployment now, and we keep a lot of parts out of this trusted computing base and only need to trust our application. And this is a great fit for the first use case I would like to briefly show you at the end of this talk, which is a use case in Germany for the electronic health records. So Germany, we now get electronic health records. We don't have all this pen and paper work anymore. And because of health data being very sensitive information, if you lose, if they get lost, it's not like you can change them, such as a credit card number or something, right? So they are very much need to be very much protected. And confidential computing allows us to even get to the point where we have a provider exclusion, right? Where whoever hosts this electronic health record system does not have access to the electronic health records themselves. And this requires very fine-grained control and very fine-grained isolation of the application that processes these health records. And right now, this is predominantly being done with the first iteration of confidential computing, which was Intel SGX. But something like confidential containers offers a great or a similar level of isolation, where we have this more fine-grained and smaller TCP. A different use case is where we just want to have lift and shift, right? We don't want to deal with isolating individual containers and applications. Maybe we just want to reduce CapEx, I don't know, make use of GPUs and move workloads to the cloud. And here there's an example of a hospital clinic as an example of a very regulated entity in Germany, right? In this case, in the healthcare sector, which wants to consume cloud computing to not build another data center maybe, or for not buying a lot of GPUs that might be outdated next year. Where, this allows them to consume the cloud with very sensitive information, but being completely isolated from the infrastructure and from the cloud provider using confidential computing, and in this case, using confidential clusters with Constellation. And last use case, very recent, very fresh, is now that we have the GPUs as well, so we can make use of confidential GPUs, of accelerators, for very specific AI cases. And one case is, of course, that I want to maybe use ChatGPT without exposing my prompts, all of the input I give to this model to the provider, let's say in this case, OpenAI. And their confidential computing allows you to isolate the actual processing party backend from the provider, let's say OpenAI, right? By basically having end-to-end encrypted prompts, where you pass in your prompt, it's being processed inside a confidential computing environment, and you get the response back without the provider ever being able to accessing the prompts or the response or anything. And one of our recent open source projects called Continuum AI, which basically provides a framework for hosting something like a ChatGPT in a confidential computing environment. All right, summary. We're pretty much at the end of this talk. What did we see? What did you learn, hopefully? First of all, get an understanding of what confidential computing is, how it works, and then how does it apply to our cloud stack when we want to protect our cloud workloads, when we are regulated industries and we want to move to the cloud and want to use confidential computing as a solution here, as a technical solution to this problem. Where could we apply this in our stack? We saw confidential containers, we saw confidential clusters, and all of the projects I've shown you, right? Constellation, Contrast, Continuum, they're all open source. You can go ahead, you can try them out, you can play with them, and see how they work and look and feel. And in the end, I gave you some practical use cases to get a bit of understanding of where is this used today, how are people benefiting for confidential computing today. Yeah, that's it. That will be the end. Do we have some questions? Sorry, I cannot hear you yet. Is it my sound?
Maybe now we were. No, it's me. That was the confidential mode enabled. Sorry. Maybe before any questions appear, and I got only one, because you talk about the encryption, right? And how can I manage the encryption keys in those solutions?
Yeah. So the encryption, the runtime encryption itself is completely handled by the processor. So that means it derives keys, session keys for every machine you start. It encrypts the pages with a fresh symmetric key, and the algorithm that implemented is decided by the hardware vendor. So far, I think all of them use AES for the encryption of the memory pages. And there's no, don't have any control about that. You have control about anything you do on top, right? Anything encryption, like I've showed in these projects, right, where you also implement the encryption in transit and at rest. This is something that you do yourself, or these projects do, and there you have options of what algorithms are used and key lengths and so forth.
I understand. Sometimes it's strange if nothing happens by my hand, but I understand the solution. Then it is always a need to be more modern sometimes.
Right.
Not the old guy. Okay. Then we are waiting maybe a few, maybe 1 minute for any question appear. And guys, if you have any, place on our chat, and Moritz will respond. You or even after, I think that you have no any clue to or any problem to contact with you directly, right? If somebody wants.
If they can feel free to reach out through any means, email, whatever. You can also open issues on the GitHub projects, anything that pleases.
And those all open source projects are open for contribution or not?
Yeah, for sure.
Of course, for sure.
Yeah.
As open source.
Right.
Sorry.
Yeah.
All right. Then, if there is no any questions, then we may to finish. If you don't mind, Moritz, or want to say something more.
No, thank you very much for listening, and yeah, please reach out if you have follow-up questions anytime.
Yeah, then thank you very much, guys, and thank you very much, Moritz, and see you later. Bye-bye.